Well, in this set of notes, we're going to be talking about sketching the curve, sketching f of x based on the first and second derivative tests. We're in sections 4.1 to 4.3, obviously, you see there. But we just finished talking about how f of x has critical points and how important it is to find those critical points. We're going to talk about a few theorems in this video and applying those theorems so that so we can use our calculus to determine important characteristics of a function f of x. And then you've got some practice problems that I'd like you to make sure you complete and then show me those answers online, and we can talk about the results of that in the next class. But let's go ahead and get started here. Let's keep going. A couple of theorems that are really important. One being the extreme value theorem, and I was having trouble earlier with this. Okay, so good, it's working. So the extreme value theorem, I want to talk about, first of all, the hypothesis of this theorem. Okay, so it's important you know those words. What's the hypothesis? F has to be continuous over a closed interval. Okay, now what that means is that you can't have any breaks in the graph. You know, a closed interval, it could be non-differentiable as well. So you're seeing this graph that I'm putting up here on the screen. It doesn't have to be differentiable for the extreme value theorem, but you can see as long as basically you're going from one point to the other without lifting your pencil, you're going to have a high point, so that's continuous over a closed interval, so the endpoints have to be defined. Then f has a maximum and a minimum value over that interval. It's kind of a common sense theorem if you think about it. To get from one point to another, it's like you can't not have a low point, you can't not have a high point. Even if you're going straight across, that's what I hear some students think about. They say, what about a straight line, a function that's constant? Well, guess what? There's a highest point, a highest y value, and a lowest y value, and with a constant function, those high and low points or values are the exact same. So even with a constant function which is continuous over a closed interval, we still have a high point and a low point. Okay? So therefore, it's important to be understanding that, and that when I say here's a function and it's continuous over this closed interval, you know there's going to be a high and a low point. So here I am Sunday morning making this video. My daughter just came in. I have no idea what I was just talking about. Anyway, let's see. Let's just take a look here. We've got different examples of what functions might look like. You have high and low points here at endpoints, max and min at endpoints, and then over here you have a maximum here in the middle, and then you have an absolute minimum there at an endpoint. So you can have any combination as long as you understand that the extreme value theorem guarantees that we're going to have a max, absolute max, and an absolute min as long as the function f, this is the hypothesis, so I didn't write that down. Here we have the hypothesis of this statement, and because we're going to use those terms later on, and then we have the conclusion, then definitely J or F, where did I get that, has a maximum and a minimum value over that interval. So hypothesis, and this is the conclusion. Okay, so important to remember. Okay, so if something is true, then we know for sure, because theorems don't need to be proved again because they've already been proven, then we know for sure that the conclusion will happen. Okay? Oh, I don't know why you're seeing that. Hold on. Hold on. Sorry, I don't know what happened there. I had a little technical difficulty there. But anyway, just to remind ourselves, critical points are points in the domain at which f prime is 0 or f prime does not exist. So those are critical points. We talked about that in the last video. Now, one thing to keep in mind that you might want to make note of is that critical points are not always max or min values. Okay, so it's not guaranteed that you're going to have a max or min just because you have a critical point. Okay, one example would be if you look at the graph of y equals x cubed, and looking at y equals x cubed, we've got the graph coming up like this. Okay, where the derivative is 3x squared. In fact, we could even draw the derivative. drawing the derivative. Come on now. Looks like that. But we'll get back to that. And then y prime is equal to 0 when x is equal to 0. So we have a horizontal tangent line right there when x is equal to 0. The slope is 0. So we do have a critical point to the graph of y equals x cubed when x is equal to 0, but you can see clearly, hopefully, that at that critical point we have neither a max nor a min. We do have an inflection point, which we'll talk about later, but again, nevertheless, no max or min values.